up and then it starts gradually going down. As it starts to dissipate and go down, it transfers the load from pore water to the soil skeleton. And the soil skeleton starts to consolidate, and that's the consolidation zone. So the pore water keeps going down, hasn't quite reached to what it used to be before, and then end of consolidation, it reaches to what it was before, which is the water table. And then we have the secondary compression or secondary consolidation or creep. Creep in solid mechanics or mechanical material is the deformations that you get due to constant load. It's different than consolidation. Consolidation, your load is changing. Your load is transferring from 0 to some amount because it's transferring from water to soil skeleton. So your sigma prime is changing. In creep, your sigma prime is constant, and that's what you see here. The water is not changing. It's the same value. Sigma prime in soil is the same value, but you get this additional settlement due to secondary consolidation or creep. Okay. So that's the process, and so I'm just going to go very quick over these, and I expect you to do this review on your own. We use the spring analogy where you apply the load first goes on the fluid and then transfers to the spring, and as this process happens, the water exits the soil system, and that's why the piston starts going down. That's why you get the consolidation settlement. You've already seen this, or no, this is a different one. So the load, initial equilibrium, then when you add the weight, and then after consolidation is over, you again reach to equilibrium. So the delta sigma, that additional load, transfers from water to soil skeleton. How do we do the test? Now on page 22. How do we do the consolidation test? We use the 1D consolidation test using the odometer or consolidometer. It's a rigid ring, you put the soil inside, there's coarse stone on top and bottom. You add the load, you wait long enough until the settlement is done, and that's your consolidation settlement. So you can go through all these calculations of how to calculate the settlement on your own or how the test is done. So let's flip the page to page 23. You keep applying the load, wait enough until it's done, and then the next load, wait enough until it's done, and then the next load, wait enough until it's done. So you do the consolidation settlement in increments, load increments. And then you unload it. You pick up the load, you wait until it's until the opposite of consolidation, so it starts to heave. It's done, and then you pick another load, wait long enough, and you pick another load, wait enough. So if you look at the horizontal axis here, effective consolidation stress keeps increasing, so every single one of those dots is a load increment. And then reaches to a certain value, and then you start unloading it, and you go back on a different line. So the slope of these lines are important. This line and this line are supposed to have a slope of CR, reconsolidation stress ratio, and the slope of this part, which is the normally consolidated part of the curve, has a slope of CC or virgin consolidation curve. That point right there gives you the maximum pre-consolidation stress, and based on that you can calculate your OCR using this equation. How do we get that point? I'm sorry, this point here gives you the sigma prime peak. So the point where you start seeing the curvature change of curvature in your curve gives you the pre-consolidation stress. How do we find that? That's shown on page 24. So there is the Casagrande method that is described here. You draw tangent lines, you find the bisect, you extend the line, and then you find a point that corresponds to the maximum curvature of this curve, and that defines the pre-consolidation stress. Let's flip the page again. I expect you to go through these on your own. They're go through all the bullet points and make sure you do the homework assignments that I uploaded on D2L from the soil mechanics node. So there are 2 assignments that I uploaded with the solutions. One of it is on the magnitude of consolidation, the other one is on the rate of consolidation. So make sure you review those. So I'm going to leave this for you to decide. This is very similar to one of those example problems that are in those uploaded assignments. But for calculating the consolidation settlement, you follow these steps, and you encounter either of these, one of these 3 cases, case 1, 2, or 3. Case 1 is when this is log of sigma prime, this is void ratio E, and you loading a normally consolidated soil. So you start from this point, you load it, you go basically along this steeper line, or the line that is characterized by a slope of C sub C. And your settlement equation is that. The second case, case 2, is when you're over-consolidated and stay over-consolidated. Very similar to the sand equations that we were just discussing an hour ago. So you have the OC part and you have the NC part. You start here, you add that extra load, but you don't reach to the pre-consolidation stress. You end up before that. So your vertical, the delta E is calculated based on the slope of the less steeper part of the curve, or the CR. So, and that becomes your consolidation settlement equation. And you can probably guess what case C is. Case C is, again, that's your normally consolidated, that's the OC curve, this is the NC curve. You start before sigma prime P, but your load is large enough that you pass the sigma prime P point. So you start OC, you end NC. Because you start on the OC part, you end on the NC part. And that's when you have to break your total delta E. This is your total delta E. You have to break it into delta E1 and delta E2. Delta E1 is calculated using the CR slope, and delta E2 is calculated using the CC slope. That's why this equation here has 2 parts. So there's that plus sign right there is because you have 2 different parts. One part corresponds to the NC loading, one part corresponds to the OC loading. Now I'm going to switch to page 28. So if you look at these case 1, 2, 3, the main parameter that you need to find out is what is CR, what is CC, right? How do we estimate those? One way is to do a consolidation test. Take a sample of the soil, bring it to the lab, do a odometer test, and find those slopes exactly what they are. But there are some empirical correlations too that you can use to get an initial estimate of what these values are. And it's always good to start with these empirical equations and see the magnitude of settlements that you get. If it's then if you realize that this is something that governs your design, then you can go back to the client and say, hey, it really matters if you really refine the CC and CR value, and that justifies for doing extra site investigation, getting samples, bringing it to lab, and doing a consolidation test. But sometimes it doesn't matter. You can just use the empirical correlations, come up with some range of settlement values, and you may realize that it doesn't really change the final design. Yes?
So on the cost, can you get kind of ballpark, and it's going to vary depending on the type of test and like I'm sure the environment, like where you're testing, but like what does like a standard like CPT or SPT test run?
So,
or is there like an average range of values or something like that?
Yeah. So I'll tell you what they depend on, and I'll give you a range. For CPT, it depends how deep they go and how many they do at the job site. Or basically, they usually charge per hour because they can do one hole and they go 100 feet deep, or they can do a bunch of holes and their costs usually takes into account their mobilization costs.
Right.
Once their equipment is at the job site, they just they drill as many as they can. Usually, they charge between $2,000 to $5,000 a day. So you can do one CPT of 100 feet long. Usually for seismic studies, we should do a lot in Portland now, because a lot of places have to bring their standards to the Oregon Resiliency Plan. So a lot of geotech firms are involved with seismic studies. And for seismic studies, you want to reach to bedrock, because that's how your seismic evaluations start. You need to know where the bedrock is. And so we oftentimes we end up doing CPTs that are pretty long and deep. So you may end up doing like just one CPT a day, and that would cost $2,000 to $5,000. SPT is a little more expensive, but it depends on whether if you want to get the sample or not, how many SPT per locations you want to get, how many tests you want to do. Just drilling a hole costs a couple $1,000, but if you want to do additional tests on, get the sample, send it to the soil lab, do sieve analysis, algebraic test, consolidation test that we have here. So one consolidation test could be between $500 to $1,000. So once you add those, because you don't want to drill just alone, you always want to get samples and do lab tests on it. So it ends up being probably close to $10,000 for probably one or two borings with the test.
Okay, thank you.
Nathan, do you?
Yeah, and it also depends on what kind of drilling you're doing. Like we're doing a barge drilling right now that's $33,000 because you gotta add the water.
Yeah, and I'm sure like the environment and like I said, depth if you're going down 20 feet as opposed to 200 feet or something like that, and all
Right.
makes big differences.
Right. The permits sometimes, if it's a contaminated site, then that's really drives the cost. And that's when you would rather to do CPT than SPT, because in SPT you're bringing that soil up to the surface and you have to figure out what to do with that contaminated soil. In CPT you're just drilling the hole and you fill it up with cement or mortar and you leave it there. But yeah, that's roughly where the cost. It's always good to keep those costs in mind, because again, we geotechs tend to complain a lot about there is not enough site investigation budget in this project, but it really it's our job to provide enough reason why we need to do more exploration. And it starts with this one. You have empirical correlations. You can't, it's bad practice to go back to the client at the first meeting and say, we want to do these advanced testing. That's, if it's an experienced client, they're not going to agree. So you have access to all these empirical equations and presumptive values that you would want to start with, and then explain to the client what is the driving factor. Is it the settlement that is going to define the project, or is the bearing capacity, or is the slope stability issue? And then based on that, we can convince why spending more money on site investigation can reduce the cost for the client on the long term. And sometimes it doesn't, and who wants to spend money on something that is not going to change the final answer. All right, any question or comment? So let's go through the last piece of this puzzle, which is how to deal with three-dimensional settlements. And I want to go back to the consolidation test, and I wish I brought the consolidometer sample here. In consolidation test that you all did in the soil mechanics lab, we have a rigid ring, right? Put the soil inside the rigid ring, you put a porous stone on top and bottom, you apply a load, and it consolidates. When it consolidates within the confinement of that rigid ring. So the settlement that it experiences is a one-dimensional settlement. It cannot expand. So now imagine, now going back to that spring analogy, that you apply a load, first it goes on water, and then soil starts to shrink and load transfers from water to the soil. Now imagine a case where that rigid ring is not rigid anymore. It's a flexible ring. So as it consolidates, it can also expand a little. Would you expect the pore water pressure dissipation be the same as the rigid ring? Probably not, and that's what drives this last piece of the consolidation settlement that we're going to talk about. If you look at this building right here, it's on clay, and one soil element underneath that building is subjected to a horizontal force and a vertical force. Because the soil has the capability of expanding laterally underneath this building, the pore water pressure is not going to be the same as if it was inside a rigid ring in a consolidometer test, because it has that flexibility to expand. Shall we?
Are we thinking that it's going to expand isotropically, radially?
Could be, yeah. Could be isotropically, radially expand. Of course, if you're at the center, it would isotropically expand. But if you're closer to the edges, it wouldn't be isotropic; it would be anisotropic. But nonetheless, it's going to expand laterally, and that expansion releases some of the pressure. So your soil, the stress that the soil feels is going to be different than what we really simulate in a 1D consolidation test in the lab. And that's our whole purpose here, how to make this connection with the real world where the soil consolidates in three-dimensional and it can expand laterally to the results of consolidation tests that we get from lab test consolidations with rigid ring. So to do that, let's look at this Tri-Axial Test example here. That's a Tri-Axial Test under sigma 3 and sigma 1, and the pore water pressure is U naught. And you remember in the Tri-Axial Test we said that the chamber pressure is equal, so sigma 1 and sigma 3 is equal around the sample, and then we increase the vertical load. This is now a very general case where you somehow have the ability to apply a different chamber pressure radially than the vertical chamber pressure. And we have some triaxial devices that can do that. So that's before loading, and then after loading, you add some delta sigma 1 vertically and some delta sigma 3 radially, horizontally. And your delta U increases by this amount. Skempton came up with this equation. This is Skempton's equation. That says the delta U that the soil will, the excess pore water pressure that will be induced in the soil due to delta sigma 1 vertically and delta sigma 3 horizontally is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. So A and B are called Skempton's parameters, Skempton's A and B values. For a saturated soil, B equals 1. That's easy, we can get rid of that. That parameter is 1. And A is a function of soil type, OCR, strain level, a lot of different things. And I don't want to get into the details of these because this is gets a little more advanced, but the A at failure versus OCR has a shape of this. So as your OCR increases, A decreases. So we can come up with these ranges for soil. So this is what I expect you to know. For clays at small strains, A ranges between 0.3 to 0.5. For A at failure ranges between 0.8 to 1.5. 1.1 for NC clays, and is essentially 0 for OC clays of 4 to 8. And in the problem examples, I'll tell you which case we are at, so then you can pick the average value from one of those cases with it. So why it ranges like that, let's leave that aside, let's not worry about it. But we basically have A and B in this equation here now. B is 1 if we're saturated, and A is one of these values depending on whether if it's NC clay or OC clay, or whether if you're evaluating at small strains or at failure. So now let's go back to the actual building analogy. So that equation, the Skempton equation, was developed for a tri-axial test. Now, in a real world situation, we can just assume that B is 1. That's your building sitting on clay. It's saturated, so I'm just going to assume B is 1. Saturated. Therefore, B is 1. So your delta U becomes now, I'm going to put the equation side by side. So we had, if B is 1, in a triaxial test, we have delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. In a real world, in this building example, B is replaced by 1, so it becomes delta sigma H, that's the horizontal stress, plus A times delta sigma V minus delta sigma H. Okay? So it's the same equation here, except now I'm writing in terms of horizontal and vertical stresses. So now, how do we calculate the three-dimensional consolidation stress? First, we calculate it for a one-dimensional case where you don't have any expansion laterally. So calculate WC, or that's the consolidation settlement, assuming 1D strain. And in that case, delta U is equal to delta sigma V. So you're confined in a rigid ring. You apply a load, and all the load goes vertically. Excuse me. So your consolidation settlement is the integral of the strain, epsilon V, and you can replace strain with mv times delta U. And if you don't remember what mv is, go back to the notes for solid mechanics. Don't get bogged down with it right now, but it's some parameter that relates the compressibility of soil to the pore water pressure. So review soil mechanics, and you can replace delta U with delta sigma V, because every load that you apply vertically goes on water, right? Goes on water first and then transfers to the soil. This is a 1D case. In a 3D case, the load that you apply vertically does not go to water all the way. It goes to water and the horizontal stress. So we correct the answer for a 3D effect by this equation, that your delta U is not just equal to delta sigma V, but it's a function of delta sigma H and delta sigma V. And you can write the equation in this form, but then here's the important thing. Again, you write the equation for WC in a 3D, so the consolidation settlement in a 3D is nothing but the integral of the strain, and the strain is mv times delta U. And now I'm going to replace delta U by this thing here. So this is replaced by delta U. So In a 1D case, delta U was just equal to delta sigma V. In a 3D case, delta U is equal to this term here. And that's basically it. What this tells you is that you can calculate something called mu, which is the ratio of consolidation in 3D versus the ratio in consolidation in 1D. And that's A plus alpha. Alpha is this delta sigma H over delta sigma V times 1 minus A. So without getting lost with how I got to this point, you can, if you got lost over there, let's just start from here. The consolidation in 3D over consolidation in 1D is equal to this ratio. That ratio is, let's say, 0.8, which means that you can calculate your 1D consolidation using all the things that we learned in solid mechanics, multiply it by that 0.8, and that gives you the consolidation in 3D. Okay? So, how do I get that pointer, or how do I calculate that value? It's a function of A, which is the Skempton A, and alpha. And alpha is this, but it's difficult to calculate it, so people simplified it for us. So for different H over D values, and whether if you're circular footing or a strip footing, alpha is given. So this table gives you alpha. So it goes from 1 to 0.25 or 1 to 0, depending on what type of footing you have. So you look at this, you get your alpha, and A is given on page 28, at the bottom of page 28. There were different ranges of A that was given, and that's, if I ask you to do this calculation, I'll tell you what A to use. And you're basically done. So in design, what you do, you calculate settlements for a 1D case. That's what you should already know. You estimate A and alpha from these values here, and you calculate that mu ratio, and then you multiply that mu by the 1D settlement, and that gives you the 3D consolidation settlement, and you're done. So now you have your 3D consolidation settlement, you have your immediate consolidation settlement, you add them together, and that gives you the total settlement underneath the foundation in a clayey soil. Any question? Robert?
Yeah, I have a quick question about the empirical correlations for CC and CR on page 28.
Yeah?
For the CC calculation, it has LL minus 10, which I would think would be the liquid limit, but here it says the liquid index, which I'm not sure is a percentage. The liquid limit is a water content, right? So that would be a percentage, but the index is...
You're right. This should be, thanks for picking that up, this should be liquid limits. In practice, sometimes people call liquid index, but I like that you picked it up because we had another parameter called liquidity index, and I don't want you to confuse this with the liquidity index. Liquidity index, you're right, was a ratio. And this thing here is just a liquid limit. It's a water content, and it's in the form of a percentage format. And it's very typical to use 1/10 or 20% of CC as a CR. This is very common too. In fact, a lot of times it's hard to get the CR from lab tests. So you might see that you send a sample to a lab test where you get the CC value, and then when you're doing your calculation, you just multiply it by 20% or 10%. That gives you the CR value, and then you do the rest of the calculation. All right, any question? All right, great. So we are done with the settlement. I think it's better to just leave all the bearing capacity for next week, so we have it all. It'll be a little cleaner in terms of note taking. So homework 3 will be extended to next Thursday, and hopefully I will see you all on Tuesday. Every Tuesday and Thursday, I wonder, am I going to make it to the class or not? I'm just haunted by everything happening. Anyway, so I'll see you next week. Have a good week. Geotechnical.